All right, this brings us to buffers and buffer solutions. Now, buffers are a very important chemistry that we need to become familiar with. If you're a biologist, you might already be familiar with the bicarbonate buffer system, which biologically in your circulatory system keeps your blood at a fairly consistent pH. The reason is if your pH biologically is not somewhere in the neighborhood of 7.36 to 7.4, slightly basic, certain chemical reactions that you need to have happen in a very regulated way or at all keep you alive. And if your pH gets too high, you go into a condition known as alkalosis, in which your pH is above that 7.4, 7.5 range, and you can get very sick from that. And the opposite direction, you could go into what we know as acidosis if your pH gets much below that 7.36. And again, you can get very sick. So buffers are important in all sorts of chemical reactions. And here's what they do. Buffers will resist changes to pH when strong acid or strong base are added. They do that by having a substantial concentration of both a weak acid and its conjugate weak base. So let's take a look at these diagrams below and just take a look at how buffers actually work. Here's your buffer, and your best buffer is going to have roughly equal amounts of weak acid and conjugate weak base. Upon the addition of, let's say, a strong acid, acids react with bases. And so the strong acid will react with the weak base in the buffer. It will drive the reaction to the left, making more of the HA. And consequently, since the weak base is reacting with the addition of the strong acid, you'll have less of the weak base at that particular point. This is going to be a large product-favored equilibrium. So it has a large K value. And so it's going to go all the way to completion. That is, all of the strong acid is going to combine with as much of the weak base as is necessary to completely consume that strong acid. The strong acid, the proton, is absorbed by the weak base relatively completely. And so that is a large K product-favored reaction. On the other hand, if we add, let's say, some strong base to our good buffer system, bases react with acids. And so the hydroxide is going to react with the weak acid, and it's going to drive the reaction to the right. It's going to deplete the concentration of the weak acid, and it's going to make more of the conjugate weak base. I swear that's an H right there. Okay, so this again is a large K product-favored reaction. The strong base will go to completion reacting with the HA as long as there's enough weak acid to absorb all of the hydroxide ion, as long as you have enough buffering capacity. And the weak acid will completely consume the addition of that small amount of strong base, making more of the weak conjugate base, and it's going to make some more water in the process. So this is essentially how buffers work. They absorb the addition of small amounts of strong acid or strong base by reacting with them. Remember that acids react with bases. And in this case, the strong acid reacts with the weak conjugate base in the buffer system, making more weak acid. So add acid, you make more weak acid. add strong acid, you make more weak acid. And on the other side, when I add strong base, bases react with acids. And so when I add strong base to a buffer system, the base reacts with the acid. It goes all the way, moves the reaction to the right because the hydroxide is going to peel the protons off of the weak acid and make more weak base. So when you add strong base, you make more weak base. When you add strong base, it reacts with the weak acid and makes more weak base. So try and find a hook somewhere in there that helps you to remember the chemistry. So in chapter 16, we talked about salts. Let's try and remember what a salt is. A salt is the product of an acid-base reaction, and they can be either the conjugate bases of weak acids like sodium and potassium salts. Here's sodium acetate, potassium acetate. You could have others, sodium fluoride, potassium fluoride, sodium carbonate, potassium carbonate, etc. And so the conjugate bases of weak acids added to some inert cation from a strong base. Then on the other side, you could have conjugate acids of weak bases like nitrate and chloride salts. You could have ammonium chloride and ammonium nitrate because the ammonium ion is the conjugate acid of ammonia. These would both be acid salts. And you could stick any inert anion here, one that's not going to react with water, with the ammonium ion, and you would have an acidic salt. What we want to use are highly soluble ions for counterions, those ions that are associated with either strong acids or strong bases. In the case of cations, those would be things like sodium cation, potassium cation. These are most typical. On the anion side, chloride, anion, nitrate, anion. You could have bromide or iodide ion. All those group 7s are good counter anions. Okay, and you could use any of the alkali metal cations. So how do you make a buffer? Part 1. How do you choose the chemicals to make a buffer? Well, the best conjugate pair for a buffer has a pKa, this guy right here, and remember that pKa is just the negative log of whatever the Ka for that particular acid is. So let's say I needed a buffer system that had a pH that was pretty close to 5. So I might go in, look at a weak acid, acetic acid. So HC2H3O2, acetic acid, has a Ka that's equal to 1.8 times 10 to the minus 5. Now, if I take the negative log, so we're going to calculate the pKa, which is equal to the negative log of 1.8 times 10 to the minus 5. That gives me a pKa of 4.74, which is pretty close to a pH of 5. What I would need to do is add a little bit more conjugate base and a little bit less of the acetic acid, and I could move that pKa up where it was closer to a pH of 5. So choosing your buffer is about choosing the acid side of the buffer choosing the weak acid side of the buffer, which has a Ka that you can take the negative log of and come up with a pKa that is close to the pH that you're interested in. I'll see if we can make that a little bit more clear. What chemicals would be the best choice for a buffer with a pH close to 4? So we're going to do exactly what we just said. We're going to calculate the pKa of all of these. This will be the negative log of 5.6 times 10 to the minus 4. And you've probably figured out this is a little less than 4. We're going to do the same thing here. We're going to calculate the pKa, which is equal to the negative log of 1.8 times 10 to the minus 4. And again, this is going to be less than 4. And then this one should be out of range if what we're looking for is a pH that's close to 4. This pKa will equal the negative log of 4.0 times 10 to the minus 8. And we know that's going to be around 7 something. All right, so here we go. All of these acids, that's how you're going to choose your buffer system. Okay, you choose the acid that has a pKa closest to the one you want. That appears to be the formic acid. And by the way, formic acid is the acid that gets injected to you. I believe it's fire ants, which burns pretty good and has a little bit of an allergic reaction in your skin, raises a little white welt. But at any rate, this is how you pick your buffer. You pick the acid with a pKa closest to the pH of interest. So how do you make a buffer? In lab, well, the easiest way would be, let's say you go to the chemical shelf and you get yourself, let's say in this case, we'll get some acetic acid, C2H3O2, and you get the salt of its conjugate base, which you might also find on the chemical shelf. And so that is one way. Don't worry about the sodium. We know that it's inert, but we've got conjugate weak base here, and we've got weak acid. And if we have equal molar amounts of these in solution, oops, this is a weak base, we're going to have our buffer system. So acetic acid and sodium acetate. We could also combine a weak base like ammonia, NH3, and its conjugate acid salt like NH4Cl, ammonium chloride. Here is the weak base. Here is its conjugate weak acid. We know the chloride ion. It's just part of a strong acid, so it's inert. But then we have the ammonium ion in solution. We have equal molar amounts of both of these. We've got our buffer. Now, it isn't always possible, depending on what the chemicals are, that you could get both sides of the buffer. For instance, you might be able to find, let's say, the weak acid HF, but no sodium fluoride or potassium fluoride. So you could take that weak acid in a reaction. So here we have HF. I'm going to add some sodium hydroxide, some strong base. Now this will be a large equilibrium constant. It's a big K, product favored reaction. Don't worry about the sodium, but the hydroxide is going to reach out, react with that hydrogen ion, peel it off. It's going to make water, and it's going to leave behind some fluoride ion. So you've made water. We don't care about the water. It's there, but we don't care about it. What do we care about is that we've made some weak base to go with our weak acid. So let's say I had a 0.1 molar solution of HF, and I come in with a 0.05 molar solution of sodium hydroxide. I generally use half as much. So that's going to be minus 0.05 minus 0.05. Our strong base is gone, but in the process, we made 0.05 molar of fluoride. So that is a typical way to make a buffer using a weak acid and adding half as much strong base with it. We could do the same thing with a weak base and neutralize half of it with strong acid. So in this particular case, we could do this. We could take ammonia, NH3, and we could add some HCl. And this is a big K all the way to products reaction. Let's say, again, we have 0.1 molar, 0.05 molar of the HCl, and the H plus from the strong acid is going to protonate that weak base. It's going to accept that proton. You're going to get NH4 plus, and you'll have some Cl minus floating around. Now, you start out with none of that, but this reaction goes all the way. And so what we wind up with is 0.05 molar of the weak base, and then we're adding 0.05 molar of the conjugate weak acid, and we now have our buffer system. So ammonia plus hydrochloric acid. I guess up here I shouldn't have used HF, which is toxic as hell. Nobody really wants to use it. You could. We're using acetic acid, so let's just use acetic acid instead. HC2H3O2 plus sodium hydroxide, and we're just doing the reaction. Strong base with weak acid, and what we're going to make over here is some sodium acetate, C2H3O2, and we'll also make some water. The deal is the sodium doesn't really count because it's a spectator ion in this reaction. And again, if we use half as much strong base, we are going to make 0.05 of the weak acid and 0.05 of the conjugate weak base. Hopefully you can follow that. So how do you make a buffer? The largest buffering capacity happens when the concentration of the conjugate pair are close to equal and concentrated. That's so that you don't exceed the buffering capacity. So they don't have to be exactly equal, but the best buffers can absorb equal amounts of both the addition of strong acid and strong base. So that's the nature of the beast. So let's talk about buffer capacity. And buffer capacity is simply the ability to absorb the most amount of the addition of strong acid and strong base. Now, if I have, let's say, a 0.50 molar concentration of my weak acid and a 0.50 molar of my conjugate weak base, that is a perfect buffer, and it's only able to absorb up to 0.5 molar of the addition of strong base or the addition of strong acid, because you'll blow out one side or the other of the buffer. If I had, let's say, 0.78 of my weak acid and let's say 6.8 of my conjugate weak base, even though they are not exactly equal concentrations, they do have a higher buffering capacity than the first example. Example 1 can absorb up to 0.5 molar addition of strong base and 0.5 molar addition of strong acid. But the second, number 2 over here, can absorb 0.78 concentration of strong base and 0.68 of strong acid, which is higher on both sides of the buffer. Even though they're not exactly equal, this is the higher buffering capacity because it's larger on both sides of the buffer, the weak acid side and the weak conjugate base side.